Good morning to all. Yesterday we have seen some theorems on limits. Today we'll see, by using that theorems we'll solve some examples. By using the limit theorems we'll see some problems on limits. Now evaluate the limits, evaluate the following limits by using limit theorems. So suppose number 1, limit of a function 2x cube minus 3x square plus 7x minus 1 as x tends to 3. We solve this problem by using the theorem limit of a function f of x plus g of x as x tends to 0 is equal to limit of a function f of x as x tends to 0 plus limit of a function g of x as x tends to 0. By using this theorem we will solve this problem. So this is 11. So we have limit as x tends to 3 of a function 2x cube minus 3x square plus 7x minus 11. So this can be written as limit as x tends to 3 2x cube minus limit as x tends to 3 3x square plus limit as x tends to 3 7x minus limit as x tends to 3 11. So what you get? This can be written as this is equal to 2 limit as x tends to 3 x cube minus 3 limit as x tends to 3 x square plus 7 limit as x tends to 3 x minus limit as x tends to 3 11. So this is equal to 2 into x tends to 3, so 3 cube minus 3 into x square. X tends to 3, so here is 3 square plus 7 is a constant function as it is. So limit as x tends to 3, in place of x we have 3 minus 11 as it is. So this is equal to 2 into 3 cube is 27 So what you get? Minus 3 into 3 square is 9 plus 7 into 3 21 minus 11. So this is equal to 2 into 27 is 54 minus 3 into 9 27 plus 21 minus 11. So we get this as a 37. And therefore, what do we get? We get limit of a function 2x cube minus 3x square plus 7x minus 11 as x tends to 3 is equal to 37. Now we see the another problem. Limit of a function as x tends to 0. Limit of a function as x tends to 0. Limit of a function 9 minus x minus 3 divided by x as x tends to 0. So we'll see the solution of this problem. This is also very easy problem. Limit of a function root 9 minus x minus 3 divided by x as x tends to 0 is equal to, this can be written in this form, limit of a function, limit as x tends to 0 of a function root 9 minus x minus 3 into root 9 minus x plus 3 divided by x as it is into root 9 minus x plus 3. We divide and multiply by 9 minus x plus 3 of this function. So what do you get? We get this is equal to a minus b, a plus b. This is in the form of a minus b, a plus b. So a square minus b square. A square is root 9 minus x into root 9 minus x is 9 minus x and minus b square is 3 square, that is 9. So this is divided by x into root 9 minus x plus 3 as it is, limit as x tends to 0. So what you get? You get this is equal to limit as x tends to 0, this will be cancelled and this x minus x upon x is a minus 1 upon root 9 minus x plus 3. So what you get? You get this is equal to, minus 1 upon root 9 minus as x tends to 0, that is in place of x we have 0 plus 3. So this is equal to minus 1 upon square root of 9 is 3 and this is plus 3 minus 0, this is plus 3 as it is. So this is equal to minus 1 by 6. This is the solution of this problem also. It is the minus 1 by 6. Now you see the another example, simple example. Now we see the another example. Limit as x tends to 2 of a function x plus 1 into 3x minus 4 divided by x minus 1 into 2x minus 3. We will solve this problem. Solution. We have limit as x tends to 2 of a function x plus 1 into 3x minus 4 divided by x minus 1 into 2x minus 3. So this can be written in this form. Limit of a function x plus 1 as x tends to 2 into limit as x tends to 2 of a function 3x minus 4 divided by limit as x tends to 2 of a function x minus 1 into limit as x tends to 2 of a function 2x minus 3. So this is equal to limit as x tends to 2 of a function x plus limit as x tends to 2 of a constant function 1 into limit as x tends to 2 of constant function 3 into limit as x tends to 2 of function x minus limit as x tends to 2 of a constant function 4 divided by limit as x tends to 2 of a function x minus limit as x tends to 2 of a constant function 1 limit as x tends to 2 of a constant function 2 into limit as x tends to 2 of a constant function x minus limit as x tends to 2 of a constant function 3. So this is equal to limit of a function x as x tends to 2 is 2 plus limit of a constant function 1 as x tends to 2 is 1 into limit of a function constant function 3 as x tends to 2 is 3 limit of a function x as x tends to 2 is 2 minus limit of a constant function 4 as x tends to 2 is 4 divided by limit of a function x as x tends to 2 is 2 minus limit of a function, limit of a constant function 1 as x tends to 2 is 1. Limit of a constant function 2 is 2 into limit of a function x as x tends to 2 is 2 into 2 minus limit of a constant function 3 as x tends to 2 is 3. So this is equal to 3 into 2 6 minus 4. 6 minus 4 is 2 divided by 2 minus 1 is 1 into 4 minus 3 is also 1. 1 into 1 is 1. So this will be, we get this is 6. Hence we solve these problems by using the theorems on limit. What about the infinity? In case of limits, we come across with infinity when domain or range or both of the function are unbounded. Accordingly, the following situations will be arise. Suppose domain of f of x is unbounded, x tends to plus or minus infinity, and function f of x tends to L. When the domain of the function f is unbounded, the variable x may be increases or decreases without bound, and this leads to the notation x tends to infinity or x tends to minus infinity. Now see the definitions. Limit of a function f of x as x tends to infinity is equal to L. This implies that, or if and only if, limit of a function f of x as x tends to infinity is equal to L, if and only if for any epsilon is greater than 0, there is m which is greater than 0 such that x is strictly greater than m, and this implies that mod f of x minus L is strictly less than epsilon. Now limit of a function f of x as x tends to minus infinity is equal to L if and only if for any epsilon is greater than 0, there is m is greater than 0 such that such that this x is strictly less than minus m. This x is strictly less than minus m implies that mod f of x minus L is strictly less than epsilon. When limit of a function f of x as x tends to infinity is equal to L, if and only if for any epsilon is greater than 0, there is m which is greater than 0 such that this x is less than minus m implies that mod f of x minus L is less than epsilon. And for x tends to infinity, x is greater than m implies that mod f of x minus L is less than epsilon. This is the domain of f of x is unbounded. This is for domain of f of x is unbounded. Now we will see for range of f of x is unbounded. Now we will see the range of f of x is unbounded. Range of f of x is unbounded. X tends to x0 and f of x tends to plus or minus infinity. Now limit of a function f of x as x tends to x0 is equal to infinity if and only if for any m is strictly greater than 0, for any m is strictly greater than 0, there is a delta which is strictly greater than 0 such that 0 is strictly less than mod x minus x0 is strictly less than delta, and this implies that f of x is greater than m. F of x is strictly greater than m. Now for limit of a function f of x as x tends to x0 is equal to minus infinity if and only if for any m is greater than 0, there is a delta is greater than 0, such that 0 is strictly less than mod x minus x0 is strictly less than delta. This implies that this f of x is strictly less than minus m. Now you see both domain and range of f of x are unbounded. Now you see the both domain and range of f of x are unbounded. Both domain f of x are unbounded, are unbounded, that is x tends to plus or minus infinity, and f of x tends to plus or minus infinity. So now we'll see the function f of x. Function f of x, limit of a function f of x as x tends to infinity, is equal to infinity if and only if for any m which is greater than 0, there is a n, and this n is greater than 0, such that x is greater than n, implies that f of x is greater than m. f of x is greater than m. In the earlier definition of limit, we use epsilon. Now this is finished. In the earlier definition of limit, we use epsilon and delta. Delta is missing, and new m is greater than m. M is greater than 0. This happening. This creates an impression that there is something special about this m. And as a matter of fact, one can write the above definition replacing m by delta. It is just by convention. We write this m. The symbols, this epsilon and this delta, are respectively related to neighborhood of limit L and x0. Here the domain is unbounded, and thus in x tends to x0 plays a role. This x0 plays a role of infinity or minus infinity. Now there is no neighborhood of x0, and hence another m is used for this delta. And in second, m plays role of epsilon, and in this third, m plays a role of epsilon and n and delta neighborhood. So now we'll see the example. Now we'll see the example. Prove that limit of a function 1 upon x plus 1 as x tends to infinity is equal to 0. Let f of x is equal to limit f of x is equal to 1 upon x plus 1. We consider this. Now this mod f of x minus 0 is equal to mod 1 upon x plus 1. X plus 1 minus 0 is 1 upon x plus 1 is equal to 1 upon x plus 1, and which is strictly less than 1 upon x. 1 upon x plus 1 is strictly less than 1 upon x. Now we choose m is equal to 1 upon epsilon, and then mod f of x minus 0 is strictly less than epsilon. If we choose m is equal to 1 upon epsilon, then this mod f of x minus, therefore what do you get? We get this 1 upon x is less than epsilon. So this mod f of x minus 0 is less than epsilon when this 1 upon x is strictly less than epsilon is equal to 1 upon m. And that means what? 1 upon x is less than epsilon is equal to 1 upon m. That is this x is strictly greater than m. This x is strictly greater than m. Because mod f of x minus 0 is less than 1 upon x, and hence for epsilon is greater than 0, there is m is greater than 0 such that x is greater than m implies that mod f of x minus 0 is strictly less than epsilon. And therefore this implies that limit of a function f of x as x tends to infinity is equal to 0. We proved this. Similarly, we will see the next example. Prove that limit as x tends to 0 of a function 1 upon mod x is equal to infinity. Let m is greater than 0 be given, and choose delta is equal to 1 upon m. Choose delta is equal to 1 upon m. Then 1 upon mod x is strictly greater than m. 1 upon mod x is strictly greater than m. Whenever this mod x is strictly less than 1 upon m, which is equal to delta. 1 upon m is equal to delta. We choose 1 upon m is equal to delta, and mod x is strictly less than 1 upon m. And therefore, hence, for any m is greater than 0, for any m is greater than 0, there is delta is greater than 0, there is delta which is greater than 0, such that this 0 is less than mod x minus 0 is less than delta, and this implies that 1 upon mod x is strictly greater than m, and therefore this implies that limit of a function 1 upon mod x as x tends to 0 is equal to infinity. We have proved this. These are very easy problems for solving. So another problem is, you keep mind these results. These are the very important results. Show that limit of a function log of mod x as x tends to 0 is equal to minus infinity. Let m, similarly, let m is greater than 0 be given. Now log of mod x is strictly less than minus m. And this implies that this mod x is strictly less than e to the power minus m. Now choose delta is equal to e to the power minus m. Then for this m is greater than 0, there exists a delta is greater than 0 such that such that 0 is less than mod x minus 0 is less than delta, and this implies that log of mod x is strictly less than minus m, and therefore this implies that limit of a function log x, limit of a function log of mod x as x tends to 0 is equal to minus infinity. This is the proof of this statement. Now, some important theorems. I will state only some important theorems for remembering you. That important theorems are some important limits also. This is some important limit or important theorems also. Some important limits. You remember these important limits or important statements. Number 1, limit of a function sin x upon x as x tends to 0 is equal to 1. You remember these statements or these formulas or these theorems. Number 2, limit of a function 1 plus x to the power 1 upon x as x tends to 0 is equal to e. Number 3, limit of a function 1 plus 1 upon x to the power x as x tends to infinity is equal to also e. Number 4, limit of a function e to the power x minus 1 upon x as x tends to 0 is equal to log a. And limit of a function x to the power n minus 1 upon x minus 1 as x tends to 1 is equal to n. Number 6, limit of a function x to the power m sin 1 upon x as x tends to 0 is equal to 0 for m is greater than 0. And a limit of a function x to the power m sin 1 upon x as x tends to 0 exists if and only if m is greater than 0. Now these are some important limits or some important results or some important formulas which are essential to learn these formulas or put in your mind. These formulas are useful for solving the problems on limits also. Okay, today we'll stop here. Tomorrow we'll see the next article. Okay, thank you.